Lab 2, motion of a falling object. The assumptions we started with were we assumed that the initial velocity is 0. This is because we are holding the object at rest, then letting it go. We are also assuming that the gravitational constant on the object by the Earth has a magnitude of 9.8 meters per second squared. The goals of this lab were to video the falling object. We tracked the motion, then modeled the motion to predict the position at a given time t. First we modeled the motion accounting for just gravity, then we accounted for drag as well as gravity. We compared our models to each other and investigated terminal velocity. We were able to model and predict the motion of the falling object using Python, and it was apparent that the drag force had to be included and accounted for the model to work. The main physics principle involved in this lab is Newton's second law. We incorporated the gravitational force and the drag force with Newton's second law to predict the motion future of the falling object. The system was a crumpled up grocery bag with a mass of 0.04 grams, 0.004 kilograms, and the surroundings were the air around the bag, which interacts with the bag to create drag force, and the earth, which exerts a gravitational force on the bag. So here we have our tracker. We started with the bag at the origin, which has the coordinates 0, 0, and the x or the y-axis going down is in the negative direction. The total time of our video was 0.708 seconds. First, we modeled the position of the trash bag with just gravity, and we did that by putting in the ball's mass, the initial position, which is 0, 0, and the ball's initial velocity, which is 0, 0, the gravitational constant, which is 9.8, the time of the video, which is 0.07 or 0.708, and the weight function here, and the total forces on the bag is just equal to the weight function. We also put in the velocity function and the position function. When we run this model, see here that the graph has an increasing slope, which means the object does not reach its terminal velocity. Then we accounted for drag as well as gravity. We kept our initial properties, and we also added in the drag force, which is proportional to the velocity squared. This is where that goes in. We also had to put some more initial conditions in here so that the program knows what the ball velocity squared and v hat are. When we compared these two programs, we saw here in blue that this is the program just accounting for velocity or for gravity, and the orange is accounting for gravity and drag, and the experimental position, which is the red dots, better fits the gravity and drag. There are a little bit of deviations from the model here, and this could be due to the shape of the trash bag and to human error. The what if question, examine the velocity versus time predicted by your models with and without drag. Which model predicts terminal velocity? The graph that predicts terminal velocity best is the gravity and drag model, because the slope here is almost the same over the time 0.45 to 0.6. When the slope is constant, that means we have a constant velocity, which is the terminal velocity. What does it mean? Imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? We can model this in our program by adding an initial velocity. So say we have -5 meters per second. When we graph this, we get the green graph, which has a similar slope to the drag and gravity model. Here they are just at different positions, but the slope is the same. So the terminal velocity is almost always the same. It does not matter whether you start with an initial velocity or not. In conclusion, we are able to predict the motion future of the falling plastic bag by modeling the effects of gravity and drag. We are also able to see that the terminal velocity for an object is the same no matter the initial velocity.